Elasticity is a fundamental property of matter that describes how a material responds to deformation when subjected to an external force. It is a measure of a material's ability to return to its original shape and size after being stretched or compressed. Here are some key properties and concepts related to elasticity. Elastic deformation. When a material is subjected to a relatively small external force, it undergoes elastic deformation. In this state, the material will change its shape and size temporarily but will return to its original shape and size when the force is removed. This behavior is described by Hooke's law. Elastic deformation is a type of mechanical deformation that occurs in a material when it is subjected to an external force but can return to its original shape and size once the force is removed. Key characteristics and concepts related to elastic deformation include Hooke's law. Hooke's law is a fundamental principle in elasticity that describes the relationship between the force applied to a material, stress, and the resulting deformation, strain. Mathematically, it is expressed as F equals K asterisk delta L, where F is the applied force, K is the material's elastic constant, and delta L is the change in length or deformation. Proportionality. Elastic deformation is typically proportional to the applied force within the elastic limit of the material. This means that if you double the force applied to an elastic material, the resulting deformation will also double, assuming the material remains within its elastic limit. Reversible. The defining characteristic of elastic deformation is that it is reversible. When the applied force is removed, the material returns to its original shape and size without any permanent change or damage. Linear elasticity. Many materials exhibit linear elasticity, meaning that the relationship between stress and strain is linear within the elastic limit. This linear relationship allows for straightforward calculations and predictions of material behavior under different loads. Applications. Elastic deformation is a crucial concept in engineering and materials science. It is used in the design of structures and components to ensure that they can withstand temporary loads without permanent damage. Understanding elastic deformation also plays a significant role in materials testing and quality control. Hooke's law is a fundamental principle in the field of mechanics and materials science that describes the relationship between the force applied to a material, stress, and the resulting deformation or change in shape, strain, of that material when it is subjected to an external force. It is named after the 17th century English scientist Robert Hooke, who made significant contributions to the fields of physics and engineering. Mathematically, Hooke's law is expressed as F equals K delta L, where F represents the applied force or load, K is the material's elastic constant, and delta L is the change in length or deformation of the material. Key points to understand about Hooke's law. Proportional relationship. Hooke's law describes a linear relationship between stress and strain for elastic materials within their elastic limit. This means that as long as the material remains within its elastic limit, the deformation is directly proportional to the applied force. Elastic materials. Hooke's law is applicable primarily to elastic materials, which can return to their original shape and size after the applied force is removed. Beyond a certain point called the elastic limit, materials may exhibit plastic deformation or permanent changes. Young's modulus. Young's modulus, E, is a specific form of the elastic constant in Hooke's law and is commonly used to describe a material's stiffness. It is defined as the ratio of stress to strain and has units of pascals (Pa) or newtons per square meter, N/m superscript 2. Applications. Hooke's law is fundamental in engineering and materials science. It is used to predict and understand how materials behave under different loads, enabling the design and analysis of structures, components, and systems. Limitations. Hooke's law is only valid within the elastic limit of a material. Beyond this limit, materials may undergo plastic deformation, and the relationship between stress and strain may become nonlinear. Elastic constants are parameters that describe the mechanical behavior of materials when subjected to different types of deformation. These constants are essential in understanding how materials respond to external forces and can help engineers and scientists predict the material's behavior under various conditions. There are several elastic constants, and they relate to different types of deformation. Here are some of the most common elastic constants and their relationships. Young's modulus, E. Young's modulus, also known as the modulus of elasticity or stiffness, describes a material's resistance to axial or longitudinal deformation. It relates stress, sigma, to strain, epsilon, with the equation, sigma equals E epsilon. Shear modulus, G. Shear modulus, also known as the modulus of rigidity, quantifies a material's resistance to shearing or transverse deformation. It relates shear stress, tau, to shear strain, gamma, with the equation, tau equals G gamma. Bulk modulus, K. Bulk modulus characterizes a material's response to volumetric compression or expansion. It relates hydrostatic stress, P, to volumetric strain, delta V/V, with the equation P equals minus K, delta V/V. Lahm's constants, lambda and mu. Lahm's constants are often used in the theory of elasticity to describe the material's behavior in terms of shear and volume changes. They are related to Young's modulus, E, shear modulus, G, and bulk modulus, K. These constants are used in stress-strain relationships and calculations for elastic materials. These elastic constants are interrelated in the context of isotropic materials. For isotropic materials, the following relationships hold: E equals 3K, 1 minus 2 nu, E equals 2G, 1 plus nu. These relationships allow you to calculate one elastic constant in terms of others, which is particularly useful when experimental data for certain constants are not available. Poisson's ratio, symbol, nu or nu(xy), is a dimensionless material property that characterizes how a material changes its shape in response to an applied axial or longitudinal deformation. Specifically, it describes the ratio of transverse, lateral, strain to axial, longitudinal, strain when a material is subjected to an axial stress. Poisson's ratio is named after the French physicist Simeon Denis Poisson, who made significant contributions to the study of elasticity. Mathematically, Poisson's ratio is defined as nu equals minus transverse. The actual key points to understand about Poisson's ratio: range of values. Poisson's ratio typically has values between -1 and 0.5. However, for most common materials, it falls in the range of 0 to 0.5. A negative value implies that the material contracts laterally when subjected to axial stretching, while a positive value implies lateral expansion. Common values: most metals have Poisson's ratios in the range of 0.25 to 0.35. Rubber and elastomers can have Poisson's ratios close to 0.5, indicating significant lateral expansion when stretched. Some advanced materials, like auxetic materials, have negative Poisson's ratios and exhibit lateral contraction during stretching. Material behavior: Poisson's ratio provides insight into a material's behavior under stress. A material with a higher Poisson's ratio tends to become narrower, contract laterally, when stretched, while a material with a lower Poisson's ratio expands laterally when stretched. Isotropic versus anisotropic materials: Poisson's ratio can vary for different materials. Some materials are isotropic, meaning they have the same properties in all directions, and their Poisson's ratios are equal in all directions. In contrast, anisotropic materials have different properties in different directions, and their Poisson's ratios may vary with direction. Applications: Poisson's ratio is essential in engineering and materials science, particularly in structural and mechanical design. It helps engineers predict how materials will behave under different loads and deformations and is crucial in designing structures to ensure stability and safety. Limitations: Poisson's ratio is a simplification and may not fully capture the complex behavior of materials, especially when they are subjected to large deformations or extreme conditions.